Okay, so 9.1, vector properties and operations. Some of you might remember some of these things from secondary one honors if you took honors. If you took secondary one regulars, this is going to be brand new for you guys. So a vector is represented geometrically as a directed line segment where the magnitude of the vector is taken by the length of the line segment and the direction is made clear using an arrowhead. If you guys have seen Despicable Me, Vector, the villain, will say that he's taken over the world with magnitude and direction. So if you want, go watch Despicable Me and you can see Vector there. Alright, so symbols to use vectors. You have it in a bolded. V, U, and W is mostly what they use for your variables. Or if you can't bold, you'll do your V, U, W with an arrow on top. Now, when we have a beginning and an end, usually they have a PQ, like a initial point and ending point. So that's going to be making sense here in a minute. So the vector drawn here has an initial point of P and a terminal point of Q. Terminal point meaning our ending point. But what happens is at that terminal point, instead of just a point, there's an arrow because we need to know that direction. Okay. Now, while it is true that P and Q completely determine V, it is important to note that since the vectors are defined in terms of magnitude and direction, any directed line segment with the same length and direction as V is considered to be the same vector. So you only have a certain length and direction of vector. So in other words, if this, or the Q was actually the initial point and P was the terminal point, because we are going in a different direction, this would no longer be vector V. Okay, that's what it's saying. Everything has its own magnitude and direction, starting and ending point. Okay. So let's talk about the component form of a vector. So when we saw above the V, U, and the W, that is in component form, okay? So the initial and the terminal are already considered in the vector, okay? So we note it by V equals, and then instead of using parentheses for vectors, we use kind of like our arrowheads. The component form of vector, where the first number is 3, is called the x component. It is not your starting or your ending, it's your x component. And the second number, 4, is called the y component. Now, technically, this would be the terminal point if we had started at 0, 0. Okay, but actually, this helps us with our magnitude. Alright, consider the vectors whose initial point is P, so 2, 3, and the terminal point is Q, and mine cut off, so I had to rewrite it, 6, 4. Oh, it's right here, that's why. Sorry, guys. But I didn't like seeing it that way. So, write V in component form. So, how do we do that? Well, let's remember that the initial point is initial x, initial y, where the terminal point is x subset 1, y subset 1. The way to find the actual component form is just to take our x subset 1 minus our initial, comma, y subset 1 minus initial. So in this case, we would have 6 minus 2 and 4 minus 3. So our V vector would be 4, 1. Using the language of the components, we have that two vectors are equal if and only if their corresponding components are equal. So in other words, if I had vector v and vector w, and I said that these two vectors were equal, that would mean both of their x's are equal and both of their y's are equal. If one thing's changed, it is not equal vectors. All right, vector addition. Suppose we are given two vectors v and w, and the sum of the resultant vectors v plus w is obtained geometrically. First plot v, next plot w so that the initial point is on the terminal side of v. To plot the vector, begin the initial point of v and the end of terminal side. So here's the idea, guys, and I'm actually going to add on to this. So if we are given v, so we would plot v first because it says v plus w. What we usually do is at that terminal side, we then start the initial of w. Okay, and so we draw that, and w ends right here from there. So that means our resulting vector is from the original, the initial on v, to where that ending is. So your very end of this addition vector, those two arrowheads would be in the same position, okay? I'm actually going to show this a little bit more in the example so you can understand how we're adding it on, okay? Now, a couple of sections ago, we learned how to do bearings, okay? So let's keep that in mind. So the first thing I'm going to do, I'm going to draw this so you're able to see what's going on, and then we'll actually answer the question of finding the true speed and the true bearing, okay? So right now, let's draw this. So I have my north, south, east, and west, okay? And we are actually going to, I'm going to say this 175 is V. Now, V, and actually I'm going to do this in another color so we can see. So purple. And this is north 40 degree east. Remember, what that means is from north, we're going 40 degrees towards the east. So that means we're going out this way. Okay? So, and we go out so far for the 175. So remember that this is 40 degrees right there. And this is vector V. Alright, let me get another color. I'm going to do the 35 as W. Okay. Now I'm going to create W by itself and then we'll attach it on after. Okay. So W is 35 miles per hour, is blowing at the bearing of south 60 degrees east. So I start at my south, but I'm going 60 degrees east. So go here. And I'm only going out so much because it's only 35 compared to that 175. So this is 60 right here. And this is W. Okay. So really, if we were to do what we did last time or up here, and we talk about adding, I should actually be adding W right onto V. So if I look at what W is doing here, I'm going to actually move that up and add it on to the terminal of V. Now, if you look, and I'm going to get another color so you guys can see this. If you look, V plus W is this vector here. Okay? All right. So now that we have what it looks like, we actually have to find the true speed, which is actually this V plus W, and then we have to find the true bearing, which is actually going to be this alpha right here, okay? So let's try to find the bearing first. So what I am going to do now is I'm actually going to draw this bigger so we can see what we're looking at. and label everything I know. Okay, so this is 175. This is 35. This is what we want. And eventually this is also what we want for alpha. Okay? Now we're missing pieces of information here. We actually have them, but we got to find them. So I want to point out that we actually have this degree right here, and I'm going to show you why right now. If we go back to this situation, look at where I put W and W. These are parallel. And if we go back to our olden days of all of our parallel lines cut by a transversal, we can go back to all of our properties. So actually, this angle here, which is what we want, is actually the same angle here. Remember, those are corresponding angles are equal when you have a transversal cutting parallel lines. Okay, so these two are actually equal. So let's look at this. Well, if you remember, this little part is 60 right here. This is 60, remember? And if we look, if we wanted this other part, well, this is vertical angles. And vertical angles are equal. So that is 40, which means this whole angle is 100 degrees. And since these two are corresponding, that angle is 100 degrees. And now we have enough information to fill out our missing spots. Can you remember what we should be looking back at? Well, if we have two side lengths and the inside angle, we are looking at law of cosines. Now, one thing I want to tell you right now, because we are in degrees, make sure if you are using your calculator, which you will be, make sure your calculator is in degrees for this one. Okay, so let's find that true speed, or C, right now. Well, if we're trying to find the side, and we're given two sides and an angle in between, we have to use law of cosines. I know this because I have no pairs. Remember, we can only use law of sines if we have pairs. So, I am going to do that now. We are missing side C. Okay, and remember, law of cosines is C squared equals A squared plus B squared minus 2, blah, 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 blah. But instead of having this squared here, I'm just going to automatically write it as a square root. Because we know to get rid of a square, we take the square root. So we get 175 squared plus 35 squared minus 2 times 175 times 35 cosine 100. Alright, awesome. And because the C is on the left side all by itself, we're able to put this straight into our calculator and not have to worry about it. So C is approximately 184. So I'm going to label that as the true speed is 184. And don't forget, we're in a situation so you want your units. So miles per hour. So that's great. We've got one of our questions done. By the way, I know it's true speed because this 175 and this 35 are also speeds. Okay, speed, speed, speed. Okay. Now, we have to find that bearing. We have to find that alpha. What are we going to do with that? Well, actually, that alpha helps us find that bearing. Let me just say. Because the bearing itself goes from either north or south. But we know we're 40 here, we're 60 here, but we need that alpha to help us, okay? So let's try to find that alpha. Let's stick with the law of cosines because, you know, we already have the formula there, so we might as well. So if you see, we actually have a pair now, okay, and we're finding alpha. So alpha goes, of course, in the cosine spot. And if alpha goes here, that means the side across from alpha goes on that left-hand side. Okay, so by the way, this is to find alpha. Okay. My kids have been watching Frozen, so I almost said Elsa. Crazy me. Alright, so we're going to have, and this time I'm going to not have the square root because I'm not solving for a side in this spot. So I'm going to have 35 squared equals 175 squared plus, now we know C, so let's go 184 squared minus 2 times 175 times 184 cosine alpha. Now remember, that degree has to be opposite to that side. So, opposites, right? Okay. Now, we have to solve. Be careful with your algebra here. Remember, we could combine these guys, subtract that over, divide that over, and then how do you get rid of cosine? Inverse cosine. Okay, so I'm going to just give you the answer right away, but if you need practice doing that, make sure you go back to your other notes, or you can try it yourself and see if you got that same answer. So when I get all through that, I end up with alpha equals 11 degrees. Okay, now that is not the true bearing. The true bearing has direction to it. So let's keep in mind, let me graph this so you can see. So my angle right here is 11 degrees, right? And this is my V plus W. So this is the one that I want to make a true bearing with, okay? So we also know that this is 40, right? So why don't I do this bearing right here? Okay, so 40 plus 11 is 51 degrees. Now, if I did 51 degrees, did I start at my north or did I start at my south? I started at my north, so north comes first, and then did I go to the west or did I go to the east? I went to the east, 51 degrees. And now this is our true bearing. Cool, guys, if you ever do aviation, all that stuff, it's going to come in handy. Alright, example 3. Alright, let V, so we're in vector component form, and suppose W, and we have our initial and our terminal point. Then we're going to find V plus W. If you guys see, we can't add a component form to a non-component form. So the first thing we're actually going to do is change W into component form. So W would be our, remember it's X subset 1 minus X initial, comma, Y subset 1 minus Y initial. So this means our component form of W is going to be 1, comma, negative 2. Alright, now I can add V plus W. So really what I'm doing, guys, is I'm saying vector 3, 4, adding with vector 1, negative 2. When you guys do this, you have to add the same components. So I'm going to add 3 and 1. 3 and 1 gives me 4. And I'm going to add 4 and negative 2, which is 2. Now, I am actually going to show you graphically how this worked. Alright, so I'm going to start with vector V. So vector V is 3, 4. So 1, 2, 3, 1, 2, 3, 4. So I'm going here. We're going to assume that it started at 0, 0. Okay, so that's vector v. Now, when I add this vector of a 1, negative 2 on it, what that's telling me is that the x component is 1, the y component is negative 2. So positive 1 means I'm going to go to the right 1. Negative 2 for the y means I'm going to go down 2. So I'm going to do that straight from the terminal of v. So I'm going to go right 1 and then down 2. 1, 2. Okay, and what do you know? Where did we end up? We ended up with this vector, and we're at 4, 2. Huh, it worked. All right, in order for vector addition to enjoy the same kind of properties as real number addition, it is necessary to extend our definition of vectors to include the 0 vector 0, 0, as I was saying before. Okay, so here are some properties of addition of vectors. We have the community property, which means we can switch. We have associate property, the identity property, and the inverse property. I actually want to prove to you the commutative property right now, okay guys? So let me see if I can draw this big enough. So we don't actually know what V and W are, so I'm going to use them in colors to make sure, in different sizes, we can make sure we can compare them. So if I said vector V was in blue, and then vector W was in red, and I'm going to go off like here, okay? That means that V plus W is this vector in pencil, okay? Now, what if I started it the other way? What if I started with W, and then I added on V to it? And what do you know? I end up at the same ending point there. So that proves to you graphically that the commutative property does work. Okay, so using the additive inverse, so it's like our subtraction, guys. The thing is, this is an extra step that I don't think you need. You can think of it like subtraction, but really, because we like the addition, what's happening is when you see the subtraction here, you're adding on the opposite of the second one, which makes sense because it's almost like you're multiplying by -1. So if we were actually doing addition right now, we would say V plus W, and then we would get our V plus W. But really what we're looking at is V minus W. So we start with V, and instead of adding W onto it like we did here, we're actually going to go in the opposite direction, and then we end up with our V minus W vector. Okay. Same thing going back and forth here, just showing that associative, well, meaning we have to, not really associative, but like meaning when we get the additive inverse, having that negative W, okay? But it will make sense more algebraically when we do that. Then we have scalar multiplication. So if we have vector V, it's just saying 2V is double that first vector. Half of V would be just half of that original vector. And then when you multiply by negative, it goes in the opposite direction. So here we have V, and we're going to multiply by negative 2V. So first we double it, and then we flip it, so it's in the opposite direction. Okay. Alright, so here's some more properties, specifically with scalar multiplication. So this is the associative, meaning you can change those parentheses around. And then we have our identity property. One is just one v is just v, almost like that one disappeared, but it's always there. We have our additive inverse, so negative v is the same thing as negative 1 times v, as I was talking earlier. Our distribution property works, distributed property works, and so does our zero property. Okay, so we're going to do some of this math here. Now, some people, when you do it by hand, make you justify each step with all of these properties. I'm not going to do that. We're just going to do the algebra step by step. Okay, and some people do the additive inverse stuff. I'm just going to distribute the negative out and things like that. So if you see here, the first thing I see is I am going to distribute this negative 2 to this vector and this vector. So I'm going to have 5v minus 2v minus 2 times the vector 1 minus 2. And then all of that equals to 0. Now remember, our goal here is to get v by itself. Well, same thing as we can do with our combining like terms, we can do that with vectors. So 5 vector v minus 2 vector v is, of course, 3 vector v. I'm going to distribute that negative 2 out, so I'm adding this negative 2 comma 4. Okay, now equals 0. Remember, the goal is to get v by itself. If this were normal numbers, we would subtract this from the other side. But I'm exactly going to do that. I'm going to subtract this vector to the other side. So I get 3v equals 0 minus vector negative 2, 4. I'm doing this, guys, because we know eventually we're going to distribute that negative out. So we end up with 3v equals 2 comma negative 4. How do you get rid of the 3? Well, we can multiply it by 1/3. We say multiply by 1/3 because we shouldn't think of division. If we said division here, divide by 3. Well, dividing by 3 is the same thing as multiplying by 1/3. So I'm going to multiply both sides by 1/3, and I get v equals 2/3 comma negative 4/3. And we just found vector v. Alright, so here's another thing we need to keep in mind. Vectors in standard position. So if any of your directions say standard position, it means the initial is at 0, 0. And we have our terminal point. Well, if it starts at 0, 0, it just means that our terminal point is actually our vector component form. Okay. The other thing is, if you look here, you go straight down, and we just created our right triangle. That means that we're going to be able to use some right triangle trig, our unit circle, all that good stuff. Alright, so here we go. We're getting into our polar stuff, guys. Suppose v is a vector with component form v equals v1, v2. Let r theta be a polar representation of the point with a rectangular coordinate v1, v2, with r being greater than or equal to 0. So here are some things we can get from it. When we talk about the magnitude of v, by the way, it's like this double absolute value sign. Okay, so anytime you see this, I want you to automatically think of magnitude. And magnitude is the same thing as we did in last section as r, and we can get this by doing the square root of v1 squared plus v2 squared. Okay, so here's some other facts. If a v does not equal 0, then the direction of the angle of v is given by theta. So this way we can take into account that vector v equals, and we can spread out the vector of the magnitude times cosine theta, comma magnitude sine theta. This is nice because of all of our trig and everything, right? All right, properties of magnitude and direction. Suppose V is a vector. So, okay, then the magnitude of V is greater than or equal to 0, and the magnitude equals to 0 if and only if V is 0. So, in other words, if we know that the magnitude has to be greater than or equal to 0, and then the magnitude is 0, that must mean that V is the 0 vector. Alright, for all scalars, K, so K is a constant. This property works, so we could do, remember, it's a constant, not a known vector, it's a constant. So if we have a magnitude and we have to multiply the vector before we take the magnitude, it will be the same as taking the magnitude and then multiplying it by the absolute value of K, right? So it's almost like the distributed property, kind of, but you have to remember K would have to be the absolute value. And then we have, if V does not equal 0, then V is the magnitude times cosine theta comma sine theta. So look at this, right? That means it's just like that distributed property. Okay. All right, let's do some examples with these. So example 5 says, find the component form of the vector V where the magnitude is 5 so that when V is plotted in standard position, it lies in the second quadrant and makes a 60-degree angle with the negative x-axis. So right there, I want to picture it. So let's draw it out. It's in the second quadrant, and we know it makes a 60-degree angle with the x-axis. Okay, so this is where our vector is. All right, so we want to find this vector in component form. Okay, so where can we start? Well, we can start knowing that we have the magnitude, right? We have the magnitude, and this isn't theta, but we can get theta because actually theta is going to be that angle. So we're going to use that the vector V can come from the magnitude times the component, or the vector of cosine theta comma sine theta. So if I put all that stuff I know in there, I get the vector is 5 times the vector of cosine, well, what's theta, guys? If this is 60, this theta must be 120, and sine 120. We can use our unit circle, memorization, whatever we need there, and we get 5 times the vector of negative 1/2, comma, square root of 3 over 2. And then we know that since we want it in component form, that vector V then is negative 5/2, comma, 5 square root of 3 over 2. And we're done. We got our vector in component form. All right, example 6. Again, let's look at what we have and what we need to find. For vector V, so we have a vector. We're finding the magnitude and theta. Okay, so then once we find the magnitude and theta, we're actually going to put it in this form. So all we have right now is this. Well, again, I always have to keep in mind what quadrant it is in. So if we look, we're down here. Okay, we're in quadrant 4. All right, so when we think of this, we have to think of changing it to polar, right? Because polar would be r comma theta. All right, so, well, how do we find r? If you remember, it said above that r is the magnitude. How do we find the magnitude? Well, we can just do that by doing r square, right? So r, which equals the magnitude, I just want to keep that in mind, which equals the square root, and it's our components here. So 3 squared plus negative 3 square root of 3 squared. When you do out that algebra, we get that it equals 6. So now we have our r, which is actually our magnitude, so that's good. Now we need our theta. Okay, well, how do we find our theta in the past? We went tangent theta equals y over x. So it's going to be our negative 3 square root of 3 over 3, which actually reduces to negative square root of 3. So let's think, in case we're not able to use our calculator here. Let's go back. So what would be our radian if we had negative square root of 3? Well, our theta would be 5 pi over 3. Okay. We don't have to worry about doing the negative. We could if we want to, but there's nothing. Oh, we actually don't want the negative. Let me prove to you why. Because it said theta has to be in between 0 and 2 pi. So in this case, we wouldn't do a negative pi over 3 because that would be outside our domain. So let's always keep the domain in check. All right. So we know our polar form is 5 pi over 3, and now we can put that into our magnitude form here. So we would get, here we go, the magnitude of v is 6, and then we would get cosine 5 pi over 3, comma, sine 5 pi over 3. And that's how they want us to leave it, guys. So this would be our answer. Learning so much today. Almost done. 2 more left. Alright. For vectors v, 3, 4, and w, 1, negative 2, find the following. Alright. So as you can see, we have vectors, but we need magnitudes. So the first thing I'm going to do is find the magnitude of v and the magnitude of w. So the magnitude of v gives me the square root of 3 squared plus 4 squared. Well, we do that math out and we get 5. We have the magnitude of w. We get the square root of 1 squared plus negative 2 squared. Now, if you do that on the calculator, don't forget your parentheses around that negative number. And we get the square root of 5. Okay, now I'm going to replace my magnitudes with our actual values. So I get 5 minus 2 square root of 5. And if we look at that, we can go no further. So that would be our answer. Last problem, guys. Yay! Alright. I want you to recognize here that v and w are in the magnitude, which, just like parentheses, means we have to do what's inside before we do the outside stuff. So actually, I'm going to look at this v minus 2w first and evaluate that. So let me write these things in here. So we have our vector 3, 4 minus 2 times 1, negative 2. All right, let's do that out. So we get 3, 4 plus negative 2, 4. Remember, when we add vectors here, we add the same component. So we're going to get 3 plus negative 2 is 1, and 4 plus 4 is 8. Alright, this is the v minus 2w. So now what we're going to have to do is take the magnitude of this, which we know is the square root of 1 squared plus 8 squared. So our answer would be the square root of 65. Awesome, guys. Good job for today.